Hello,
Hello, sir.
how are you?
Fine, sir.
Okay, so any doubt from last
Oh,
class?
no, sir.
Okay, just 1 minute. The last part of this chapter is on basis of Bernoulli's principle is Torres-Lee law. It simply defines velocity of E flux. So what do you mean by E flux? I'll define it. Just 1 minute. Suppose I'm initially considering any closed tank. Another hole is cut out at this point. Level of liquid in this particular tank is up to this mark. Height of level of liquid from this point to this point is capital H. And let's say velocity of liquid ejecting out through this particular hole, the hit on the ground at this point is VE. This velocity of ejection of liquid through this orifice is called velocity of efflux. Is it clear?
Yes, sir.
Now, suppose position of hole from this point is H. So height from bottom is H minus H. Let's say there is some pressure inside and pressure outside P naught. So you have to apply Bernoulli's principle. So I'm assuming this particular part in the shape of tank or a tube like this, whose one end is at this point and the next end is at this point. Is it clear?
Yes, sir.
So let's say this is first end and this is second end. At first end, since area is very large, so level of liquid falling down will be very small. Just 1 minute, Harsh.
Okay, sir.
Harsh. Okay, so we have to prove this particular part. So let me define you how to solve. Consider a closed tank in which liquid is filled up to H. A hole is cut out at H below the surface of liquid from the top through which liquid is ejecting out at velocity VE. So we have to calculate expression of velocity ejecting out through this particular part. Since at first hand, area of cross section is very large, so velocity of falling liquid or velocity of decrease in level of liquid at this point will be very small or simply equivalent to 0. Is it clear?
Yes, sir.
So according to Bernoulli's principle, pressure at point first plus kinetic energy per unit volume at point first and potential energy per unit volume should be equals to P2 plus half rho V2 plus rho G H2.
H2.
Now put the values of each term in this part. P1 is Pi. V1 is almost 0, so it will be 0. Rho G H1 is capital H. P2 is pressure outside of this tank, so it will be
PO.
P naught plus half rho velocity of ejecting liquid at second point is VE, and rho G H2 is
H2.
H minus small h. Is it clear?
Yes, sir.
Now just simplify it. Move this P naught to left side. So you'll get Pi minus P naught
P naught.
plus rho GH. Move this rho GH part to left side. So you'll get minus of rho G capital H and plus rho G small h equals to half rho VE square. This quantity and this quantity will get cancelled out. So on solving, you will get velocity of efflux equals to 2gh plus 2 times change in pressure divided by density root under. So this is our final expression of velocity of ejecting out through this particular hole. Is it clear?
Yes, sir.
This velocity of ejecting liquid is called velocity of
Well,
efflux. Just write it down.
Done, sir.
Now we have to simplify this particular result for terms of open tank. Now for open tank, suppose level of liquid initially is at this point and velocity of liquid ejecting out through this hole is VE. Height of tank is H and height of position of hole is small h, and this is position of hole from ground, same term. So in this case, Pi for this, Pi will equals to P naught. Since this part is also exposed to atmosphere and this part is also exposed to atmosphere. So Pi and P naught both becomes equal. So if you put this part in the above expression, you will get velocity of efflux equals to root under 2gh plus Pi minus P naught. Both are equal, so the difference will be 0. So you're left with just root under 2gh. Harsh, is it clear?
Yes, sir.
Now, question is, what is special behind this particular relation? So let me define you. Suppose you have any body initially at this point falling under the effect of gravity alone to reach at this point through height h. So while dropping, its initial velocity would be 0. At this point, it may have attained some velocity v. So according to third equation of motion, we may write v square equals to u square plus 2as. Is it clear?
Yes, sir.
Since initial velocity is 0, so this part will be 0. So you're left with v equals to root under 2gh.
2gh.
Is it clear?
Yes, sir.
Now just compare these two results. Are they equal or not?
Yes, they are.
So we can say from this part, the velocity of liquid ejecting out through this hole is behaving as free falling under the effect of gravity and may attain same velocity as if a body under free fall during gravity. Is it clear?
Yes, sir.
So this is the special condition of this particular part. Hence, we can say, hence, it behaves as free falling body under gravity. So it will have same velocity as free falling body. Now, related to this expression, let's say this is y-axis and this is x-axis. Hole is initially at this point. Position of hole from the ground is h minus h.
Yes.
and liquid is ejecting horizontally towards this direction at some velocity VE. So it may follow this parabolic path to reach the ground or to hit the ground at this point, which is similar to projectile motion, what we did in chapter 4. Is it clear?
Yes, sir.
So this is velocity of efflux. This is total horizontal distance traveled along x-axis, which will be termed as range. So from this part, we have two different direction of motion. First is along x-axis and second is along y-axis. Along x-axis, initial velocity is VE and acceleration along x-axis is 0. Along y-axis, initial velocity is 0 and acceleration along y-axis is gravity. So we have to calculate displacement along x-axis and y-axis. So using second equation of motion, S is equals to ut plus half at square. Since a is 0, so it will be 0.
0.
So this x will be in terms of this velocity of efflux multiplied by time taken. Now, in this part, along y-axis, Vy S equals to ut plus half a t square. Y for this particular term, that is total height or height of hole from the ground, is h minus h. So on rearranging, you'll get 2 times h minus h divided by gravity root under. So this particular term will be called as time of flight. So if you put this part in this expression, so range will be equals to velocity of efflux, that is root 2gh times time of flight root under 2 times h minus h divided by gravity. Gravity cancel out, 2 and 2 taken outside as square root. So you're left with h multiplied by h minus h. Is it clear?
Yes, sir.
Now, further related to this expression, you'll be asked, what will be the condition for maximum range? So how to define maximum or minimum of a particular function? Do you know any mathematical idea behind it?
Maximum.
Whenever you have to calculate maximum or minimum of a particular function, whether it will be time dependent, position dependent, any variable dependent function, just differentiate it and put it equals to 0. So remember this particular result. For maximum or minimum of any function, just differentiate that particular part
And is equal
and
to
put it to 0.
Yeah.
It will define you the maximum or minimum value related to those different parts. Similarly, in this part, if we have to calculate maximum range, so just differentiate this range with respect to a small h, which is variable in this part, and put it to 0. So for maximum range, differentiation of range with respect to height and equating it to 0, you will get h equals to h by 2. It means holes should be met at the midpoint of tank to get maximum range. So if you put the small h to be this in the above expression, range maximum will equals to capital H. Is it clear?
Yes, sir.
So you'll be asked, suppose a tank is of 2-meter high. Where should a hole should be cut out to have maximum range? So you'll say at the midpoint of it. Good. And what should be the maximum range related to this part? So it will be just equal to the level of liquid in the tank. Okay, just write it down.
Yes, sir. So can you scroll down? Done, sir.
Any doubt?
No, sir. Sir, so today only like we will start the thermal properties of it.
Yes.
So, sir, today we'll start thermal properties of matter.
Yeah. Just in 5 minutes.
Okay, sir.
Now, from this part, you'll be asked, what will happen to the velocity of ejecting liquid when the whole tank is allowed to fall freely under the effect of gravity? If whole tank is allowed to fall freely under gravity. So in this part, what will be net acceleration? Under free fall, net acceleration of that particular body will be zero.
Zero.
So velocity of efflux in this case will be zero.
Zero.
It means no liquid will eject out from that hole.
From the
Is
hole,
it
yeah.
clear?
Yes, sir.
Okay. Next. Suppose there is a tank and there is a hole at this point in which level of liquid is up to this point. So while ejecting out, level of liquid may decrease from this initial level to some final level in change of some time. So you'll be asked how much time it will take to change its level. Let's say its initial level is this, and it may fall up to this part only. Final level of liquid, let's say, is at this point. So how much time it will take to fall down level of liquid from HI to HF? So next I'm defining you time taken by liquid to fall down from HI to HF. So for this part, time equals to A2 divided by E1 root under 2 divided by gravity bracket root under HI minus HF. I've just derived this particular result using equation of continuity. So just remember this particular formula. Whenever you have to calculate or you have to find time taken to fall level of liquid from one point to another, you may use this expression. So what is A1, A2?
Area of the hole?
Area of the hole and area of the tank at two different cents. Okay?
Yes, sir.
Just write it down.
Yes, sir.
So this will be E1 and this will be E2.
Yes, sir. Done, sir.
Okay, so this is the last part of this fluid which we have just completed. So next is end out related to last chapter.
No, sir.
Okay, so let's start with thermal properties of matter. Thermal property of matter. In this, first we define what do you mean by temperature. Harsh,
Yes, sir.
any idea?
Yes, sir. The degree of hotness and coldness of any subject. Of any.
Good. It simply defines the relative hot or relative cold of a particular object with respect to some reference. So it is basically the measure of degree of hotness or coldness of a body. So to calculate this particular part, its SI unit is Kelvin,
Kelvin.
and we use thermometer to measure it.
Yes, sir.
Thermometer measures temperature. Mainly, we have two different types of thermometer. First is called clinical and second one is called laboratory. Clinical thermometer and
Laboratory.
laboratory thermometer. Clinical thermometer ranges to the body temperature of human being, that is from 35 degrees Celsius to 42 degrees Celsius only. In between human body temperature. Laboratory thermometer ranges between boiling point and melting point of ice and water respectively.
Yes, sir.
So it is
Zero
based
to
on
100.
good melting point,
Of
which is also called ice point, 0 degrees Celsius, and boiling point or simply steam point,
steam vapor, yeah. 100 degrees Celsius.
100 degrees Celsius. So we have to define for this laboratory thermometer on what principle it is based on. So in general, for all different laboratory thermometer, we use simple scale T minus LFP divided by UFP minus LFP is equals to constant. In this part, T is called temperature on scale. On that scale, simply LFP is called lower fixed
Fixed temp.
point,
Fixed point.
which is also called ice point or melting point of ice. UFP is called
Upper fixed
upper
point.
fixed point, which
Boiling
is
point.
steam point or boiling point of water. Is it clear?
Yes, sir.
Now, related to this part, let me define you different scale. So first is for Kelvin scale, it will be K minus 273 divided by 373 minus 273 equals to, for Fahrenheit, it will be F minus 32 divided by 212 minus 32. For Celsius, it will be C minus 0 divided by 100 minus 0.
0.
For resistance like platinum wire, which may behave linear like this. So resistance offered at some temperature C, resistance at 0 degrees Celsius, resistance at 100 and resistance at 0. Similarly, length of column of liquid, mercury in a particular thermometer, length at temperature C, length at 0 degrees Celsius, length at 100 degrees Celsius, and length at 0 degrees Celsius, and so on. We may define different scale related to this given formula. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay, now related to this part, first question will be, find temperature at which first Kelvin equals to Fahrenheit numerically, and second Fahrenheit equals to Celsius. Harsh, is it clear?
Yes,
so we
sir.
have to calculate that particular part. So how to calculate? Use the above expression, put in place of k and in place of f, x and x on both sides. So you may write the above expression as x minus 273 divided by 373 minus 273
-3.
equals to, in place of f, it will be also x minus 32
32 by
divided
212
by 212 minus
minus
32.
32.
Just simplify this and you'll get the value of x. Similarly, for Fahrenheit to be equals to Celsius, put each term to be y and simplify it for the above expression. Try to solve.
Okay. Okay, sir.
Harsh, any doubt?
No, sir.
Okay.
So what's the answer for the first one?
Yes.
What's the answer for the first one?
574.25.
574.25.
Yeah. What you got?
I got 459.
Okay. Let me solve. If you simplify this particular part, x minus 273 divided by 373 minus 273, it will be 100
100.
equals to x minus 2 divided by 212 minus 32, it will be 180.
180, yeah.
This 0 and this 0 will cancel out.
Yeah.
Now just cross multiply. So 18x minus 18 into 273 equals to 10x minus 320. Is it clear?
Yes, sir.
Now move this 10x to left side and this part to right side. So 18x minus 10x equals to, just multiply this part, 18 into 3, 54,
54.
18 to 7, 126
1,
plus
1,
5, 131,
131.
and 36 plus 13, it will be 49,
49.
minus 320. So 18 minus 10, it will be
8.
8x, and just subtract it part. 4 minus 0, it will be 4.
4.
11 minus 2, 9.
9.
9 minus, or simply 8
Sorry.
minus 3, it will be 5.
5.
4. So x equals to 4594 divided by 8. 8 into 5, 40. 5, 9. 8 into 7,
8.
56. 3, 2. 8 into 4, 32. 2, 5. Is it clear?
Yes, sir. 1 minute. I'll check. Something is wrong. Yes, done.
Similarly, you may find the second part. So it will be y minus 32 divided by 212 minus 32, it will be 180. Y divided by 100. So this and this part will cancel out. Just cross multiply. 10y minus
Plus 320.
320.
Yeah. And 18y.
Move this 10y to right side. So minus of 320 equals to
8y.
18 minus 10,
8y.
8y. So y equals to minus of 320 divided by 8. That will be minus 40.
Minus 40, yes.
So this is how to calculate this particular temperature.
Done, sir.
Okay. Another question related to this concept will be, suppose a 40 thermometer reads ice point as 5 degrees Celsius and steam point as 95 degrees Celsius. Find the reading of 60 degrees Celsius on this scale. Let me define you how to solve this part. In this question, we have two different thermometers. One is water thermometer and the other is Celsius scale. So you may write in left hand side 40 thermometer and right hand side Celsius scale. So according to the above formula, temperature on 40 thermometer minus lower fixed point divided by upper fixed point minus lower fixed point must equals to temperature on Celsius scale minus lower fixed point divided by upper fixed point minus lower fixed point. Is it clear?
Yes, sir.
Now, for this question, we have to calculate 60 degrees Celsius reading on 40 thermometer. It means temperature on Celsius scale is
Should
given
be 60.
60 degrees Celsius, for
Yeah.
which we have to calculate temperature on 40 thermometer. Okay,
Yes, sir.
just try to simplify it.
Okay.
Harsh, you got any
Yes, sir.
answer?
No, sir, I'm doing it.
Okay. Ask me if you have any doubt.
Sir, I'm getting decimals.
Okay, just 1 minute. Let me define you how to simplify it. First, we have to calculate temperature on 40 thermometer. Keep it as
Yes.
it is, -5. Just solve this denominator part. So 95 minus 5,
90, 90,
90 equals to
60
60 divided
minus,
by,
yeah, 60 by 100.
now move this 90 to right side. So you may write temperature on 40 minus 5 equals to
60
60,
into 90.
90
Get
divided by
100.
100.
Yeah.
This part and this part will cancel out with this and this.
So 54, sir.
Good. So temperature on 40 thermometer, which you have to calculate, move this 5 to right side. So it will move to
59.
good. Where you have done mistake.
Sir, I took the 5 also, that's the thing.
Okay.
Done, sir.
Okay. This is the introductory part of this part. So next is thermal expansion. So first question related to this part will be why solid would expand on heating. Do you have any clue behind it?
Sir,
Why
because
solid
the
expand? Yes.
sir, because the particles expand inside the solid, like separate.
Why
Due to heat.
particle expand?
Due to heat.
Why?
Due to excess heat.
Suppose at low temperature, there will be lesser gap in between particle. So particle would arrange like this in a particular solid. Let's say at some low temperature. So if you raise the temperature of this particular body, on increasing temperature, bond gets weakened. So separation between particle increases. Is it clear?
Yes, sir.
Due to this, there will be large gap in between particle like this.
Yes.
And similarly along this way also. Hence, initially it was up to this dimension at low temperature. Now on increasing temperature, it may increases to this part. So we'll say on increasing temperature, thermal energy of particle increases, bond get weakened, and hence separation between particle increases, so solid get expand on heating. Is it clear?
Yes, sir.
So we have to define this particular expansion in 3 different ways. First is along length, linear expansion, then along area, surface expansion or radial expansion, and then along volumetric, cubical or volumetric expansion. So first is linear expansion. Suppose there is a rod initially at low temperature T naught having length L naught from this point to this point. If you increase the temperature of this particular part, so it may extend up to this to acquire length L. At temperature T. So from this point to this point, change in or elongation in length is delta L. So to define this particular elongation or change in length, we may introduce a constant quantity alpha, which is called temperature coefficient of linear expansion. So this alpha is also equals to delta L divided by L naught times delta T. So related to this part, its SI unit will be Kelvin inverse or degree Celsius inverse. Is it clear?
Yes, sir.
So from this relation, we may define this part as delta L by L naught is fractional change in length and delta T is
Change in time.
change in temperature.
Oh, sorry, temperature, not time.
So it is a ratio of these two different quantities. So we may define this alpha as the ratio of fractional change in length to the change in temperature is called alpha or temperature coefficient of linear expansion. It simply defines at what rate length would expand or contract with respect to change in temperature. So it defines the rate of expansion or compression in length with respect to change in temperature. Harsh, is it clear?
Yes, sir.
So if you expand this particular relation, you'll get as alpha equals to delta L divided by L naught times delta T. Just cross multiply, you'll get delta L equals to L naught alpha delta T. Delta L is L minus L naught equals to L naught alpha delta T. Move this L naught to right side. So you may write L naught plus L naught alpha delta T. Take L naught as common. So you're left with 1 plus alpha delta T equals to final length L. So this is your final expression of getting length at any change in temperature delta T. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay. Now related to this part, a rod is 1 meter at 27 degrees Celsius. Find temperature at which its length would become 101 centimeter if alpha is 2 into 10 to the power minus 4 Kelvin inverse. Just use the above relation and try to find new temperature. Okay. Let me give you some hint related to this part. You say this 27 degrees Celsius is its initial temperature. So T naught is 27 degrees Celsius. Keep it
Yes.
as it is. Next, length at this temperature is L naught, which is 1
1
meter.
meter. 1 meter.
Final length we have 101 centimeter. So you may write 1.01
1.01 meter.
and alpha is 2 into 10 to the power minus 4 Kelvin inverse. Just put the above formula and try to find final temperature. Okay.
Okay. So,
Yes,
so what's the answer?
I think 77 degrees Celsius. Okay, just see how to solve this part. According to the formula, alpha equals to delta L divided by L naught delta T. So move the delta T to left side and alpha to right side. So you may write delta T equals to change in length by initial length times alpha. Is it clear?
Yes, sir.
Delta T, we have T minus initial temperature. Delta L is change in length. So it will be 0.01 divide by actual length 1. Alpha is 2 into 10 to the power minus 4. Is it clear?
Yes, sir.
So you may write this 0.01 as 10 to the power minus 2. If you move this part to numerator, you will get 10 to the power plus 4 divided by 2. So it will be 100 divided by 2, that will be 50. So final temperature will be 50 plus 27, it will be 77 degrees Celsius. Where you did mistake.
Sir, I didn't know the mistake. Like I was stuck. I was like thinking, is this correct or not?
Okay, no problem.
Done, sir.
Okay. There will be some concept related to this expression as Harsh.
Yes, sir.
Okay. So next is related to this part as alpha equals to delta L divided by L naught delta T. So you may write delta L divided by L naught equals to alpha times delta T. This quantity, change in length with respect to its original length, is also called strain. And since in this expression, it is due to change in temperature, so we can call it as thermal strain. So you'll be asked to calculate thermal strain. So it will be equals to alpha times delta T. Okay.
Yes, sir.
Next is according to concept of Young's modulus, Y equals to stress divided by strain. So stress or thermal stress equals to Y times thermal strain. So it will be alpha times delta T. Now stress equals to force per unit area. So force exerted will be Y A alpha times delta T. So you may ask to find these two different expressions related to change in temperature. Okay.
Yes, sir.
Now next concept will be by metallic strip. Suppose you have a rod this, another rod this, are attached at some lower temperature, let's say T0. Coefficient of linear expansion of this is alpha 1 and coefficient of linear expansion of this is alpha 2. Suppose alpha 2 is greater than alpha 1. So what will happen if you increase the temperature of system or decrease the temperature of system? So first, if temperature is increased, and second, if temperature gets decreased. Will there be any change in shape, Harsh?
Change in shape. If, sir, if temperature increases,
Yeah.
there will be expansion.
Let me define you. This alpha simply defines you the rate of expansion or rate of compression with change in temperature. Since alpha 2 is greater than alpha 1, so on changing by same amount of temperature, there will be more expansion in second rod as compared to first rod.
Yes,
Is
sir.
it clear?
Yes, sir.
So it will tend to bend like this. So in this part, the inner surface is concave side and it is towards convex side.
Convex.
Similarly, on decreasing temperature, there will be more compression having substance, more temperature coefficient, that is alpha 2. Since alpha 2 is greater than alpha 1, so there will be more compression in second rod, that is in red rod, as compared to blue one. So related to this part, the shape of this bimetallic strip will be like this. So it will be towards convex side in this part. And the red one will be towards concave side.
Concave side.
So from this part, we may conclude greater the value of
alpha,
there will be more expansion
while heating.
as well as compression on increasing
the temp
or decreasing
the temperature.
So on increasing temperature, there will be more expansion in length, and on decreasing temperature, there will be more compression in length as well. Is it clear?
Yes, sir.
So more expansion on increasing temperature, and similarly, there will be more compression on decreasing temperature. Harsh, any doubt?
No, sir.
Okay. Just write it down.
So I'm gonna scroll down. Done, sir.
Next concept related to this part will be pendulum clock. Suppose a pendulum clock is designed to work with oscillation of pendulum, that is when it oscillates from this point to this point, that is half oscillation, it will take 1 second. On returning back to its original position again, it will take 1 second. During this oscillation, the reading of clock will be from this point, just 1 tick and the next one. It means the reading of clock will be 2 seconds for this particular part. Is it clear?
Yes, sir.
Now, at temperature T naught or just theta naught, I'm calculating. At temperature theta naught, length will be L naught. So time period will be equals to 2 pi root under L by G. So this is time period of oscillation of this particular pendulum at this temperature theta naught. Now what will happen if you increase or decrease the temperature of this particular system? Let's say at temperature theta, length will become L naught 1 plus alpha times change in temperature delta theta. Okay.
Theta.
So time period will be equals to 2 pi root under L by G. On putting the value of L, you will get root under L naught 1 plus alpha times delta theta divided by gravity. This is your final time at any temperature theta, and this is initial at any temperature theta naught. So if you divide these two different expressions, on dividing, T over T naught equals to 2 pi under root L naught by G will cancel out. So you're left with 1 plus alpha times delta theta to the power half. Rest of all other term will get cancelled out. Okay. Now, according to binomial expansion, we may write 1 plus x to the power n equals to 1 plus n times x if x is very, very small as compared to 1. Okay. So this exponential would get multiplied with this coefficient. So we may write t over t naught equals to 1 plus half alpha delta theta. Harsh, is it clear?
Yes, sir.
Now, on simplifying it, move this one to left side. So t over t naught minus 1 equals to half alpha delta theta. Take out LCM as t naught. So you may write delta t equals to half alpha t naught times delta theta.
Delta theta.
So this is final expression of getting change in time for this particular duration theta t naught. So this delta t will define you change in time. It will be gain or loss depending upon whether temperature is increasing or decreasing. Alpha is temperature coefficient of linear expansion. Temperature coefficient of linear expansion. T naught is duration of time for which we are calculating. Duration of time. And delta theta is change in temperature. Is it clear?
Yes, sir.
Okay, first write it down to this part, then I'm defining a different problem.
Done, sir.
Okay. Now, related to this part, you'll be asked, what will happen if you increase the temperature, or what will happen if you decrease the temperature? So let me define you this particular result in two different conditions. First, if temperature is increased, and second, if temperature is decreased. First part, if temperature is increased. So increasing temperature will tend to increase the length of pendulum or string from this point to this point. So increasing temperature will increase its length, and consequently time period of oscillation will also increases. Is it clear?
Yes, sir.
It means it will take from this point to this point. Initially, it was taking only 1 second. Now in this part, it would take, suppose, 1.1 second to reach at this point. And further, on returning back to this point, it will take 1.1 second. So in total, it is taking 2.2 seconds to oscillate one complete oscillation. But the reading of clock just depends upon oscillation part. That is, on going from one end to the other end, it may read 1 tick, and then on returning back, it may read 1 tick again. So in total, it will read just 2 seconds, but the total duration of time for this path is 2.2 seconds. Is it clear?
Yes, sir.
So from this, we can say reading of clock is decreasing, since it is measuring lower amount of time as compared to its actual duration. Hence, we can say a reading of clock decreases on increasing temperature.
Temperature. So on decreasing, it will be inverse, right? It will
Good.
increase.
If it decreases the temperature, length of pendulum also decreases.
Yes.
So time period of oscillation would also decreases. It means on going from this point to this point, initially it was taking only 1 second to reach at this point. Now it would take 0.9 second. And similarly on returning back, it would take again 0.9 second. During this interval, clock will read 1 tick and 2 tick, just 2 seconds. Since reading of clock depends upon number of oscillation, not their time period. So total time taken by this oscillation is 1.8 second, but the reading of clock is 2 seconds. It means it is increasing. Okay.
Yes, sir.
So reading of clock in this part
Increases.
increases. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay. A pendulum clock loses 12 seconds in 1 day at 40 degrees Celsius and gains 4 seconds in a day at 20 degrees Celsius. Find temperature at which it will read correctly, or it will show correct reading. So according to the above formula, we
Sir,
may write, yes,
is the answer 30 degrees Celsius?
no,
Okay.
delta T equals to half alpha T naught times change in temperature. Okay. So this delta T defines you how much time will gain or loss related to this T naught duration of time. So
Yes,
in
sir.
first part, 12 seconds equals to half alpha duration of time is 1 day when temperature is raised to 40 degrees Celsius. So it will be 40 minus initial temperature theta naught. Again, at some low temperature, it will gain 4 seconds in 1 day when difference of temperature will be theta naught minus 20. Now to solve this part, just divide these two expressions and simplify it for theta naught.
Sir, yes.
Harsh, is it clear?
Sir. Yes, sir. So just divide the expression with theta naught.
No, just divide these two expressions and just check which of those two quantities which are numerator and denominator would can cancel out. Let me solve
So like
simply.
4, like then it 4 will
This
cancel
part
out
and
and
this,
become like, yeah,
yes, 4 will cancel
and
out
then
12
3,
in 3 times.
3, yeah, and then
Alpha and
half, yeah, alpha is gone. 1 day is gone.
yeah. So
Okay,
just
then it's
cross
just
multiply and simplify it.
okay, sir. Sir, theta naught is 25.
Good. Now, if you put theta naught in any of the expression, you will be able to calculate alpha as well. Suppose I'm using the second one. 4 equals to half alpha. Suppose we have to calculate. And in 1 day, total duration of time in second will be 24 hours multiplied by 60 into 60. Theta naught is 25 degrees Celsius minus 20. So on solving, it will be alpha equals to 4 into 2 divide by 24 into 60 into 60. 3600
Yeah.
into 5. So 2 into 4, 8, into 3 times it will be 24.
24.
And 3 into 5 it will be 15, or simply 36 into 5 it will be 180 multiplied by 3. So it will be 1 divided by 540000. Just simplify this, you'll get alpha. So alpha will be equals to 1 divided by 54000, or 1.85 into 10 to the power minus 5. Kelvin inverse or Celsius inverse. Harsh, is it clear?
Yes, sir.
Okay, just write it down.
Yes. Done, sir.
Any doubt up to this part?
No, sir.
Okay, so let's stop here for today. In next class, we'll
Okay.
start with aerial expansion, volumetric expansion.